today's lecture is going to pick up exactly where lecture 24 left off, where if you remember in that lecture, we talked about the transformation of A to B in a porous catalyst particle. We started to really consider the mass transport of reactants from the outside of the catalyst particle, right, to the inside, and trying to figure out how we could describe the concentration gradient and the rate of mass transport in that structure. And in that lecture, we derived an equation, right, which I show right there, where C is defined as the concentration of A divided by the concentration at the surface, and lambda here is just where you are in the particle. So you can be at the middle here, right, which would be little r equal to 0, or you could be as far as this edge, which is where little r is equal to capital R. And the reason we did that derivation was that we really wanted to get to this parameter, the Thiele modulus. And the Thiele modulus was related to basically the rate of the surface reaction, or how good the kinetics were, divided by the diffusional rate. And we had a conversation last time trying to visualize how the Thiele modulus, or the value, influences how well you are taking advantage of the internal active area. Okay, and to do that, we drew a picture, and that picture had these bounds where lambda was bound by 0 and 1, right? Because you can only go from the middle to the outer edge of the particle, and also C was also bound by 0 and 1, because this is basically the concentration is equal to the bulk concentration, or sorry, the concentration of A at the surface. And that is where the concentration at a given location would be equal to 0. And then we solved, we really discussed a few cases, right? One was when you would have a very small value for this Thiele modulus. And when that's the case, what that really means is that the rate of reaction is slower than the diffusional rate, or you can provide reactants at the rate that they are desired, right, at the catalyst surface. And because of that, there really isn't much of a concentration gradient when you have small values for the Thiele modulus. And in fact, that line can be pretty flat. We also talked about other cases where, let's say that we had a very large Thiele modulus. And what that meant was that the rate of the surface reaction was faster than the reactant could be provided by mass transport, and specifically by diffusion inside of this particle here. And when that's the case, of course, the concentration in the middle of the particle, it can be almost nil if it's a very, very severe limitation. And in fact, you can have some situations where you don't even really utilize the inside of the particle at all. And so very large values of the Thiele modulus can lead to very, very poor internal utilization. And that's really the difference between these. If you really think about it as the area under the curve, right? When this area here is equal to 1, right? All of this, that means that the inside of the catalyst is utilized very, very well. When you have this area on this plot, which here, I guess that's almost 0, is much, much less than 1. All that it means is that you have very, very poor catalyst utilization, okay? And there are all sorts of other things that we could look at as well. I mean, we could look at various intermediate values for the Thiele modulus that range everywhere from maybe you're just barely at the concentration is equal to 0 to a situation where both internal and external mass transport, might play a role, right? Or there's some balance at least between those things. And so what we can see here from our discussion in the last lecture and then the first, 5 minutes or so of class today is that this plot really means that typically not all of the catalyst is utilized. And we need to have some measurement for how effectively this is utilized. And the area under the curve I showed a minute ago, fine, that might be one way to do it, but you don't have this curve, right? This is just a theoretical construct. And you don't want to have to do all of this math every time that you change something. And so what are we going to do? Well, in our case, we are going to define two effectiveness factors, okay? So one is defined as the overall rate of reaction divided by the rate of reaction without any internal mass transport problems. Or how about without any limitations in internal mass transport? Or relating it to the plot above, usually we would have a pretty small Thiele modulus. And of course, another way to think about that is that the concentration is inside the particle everywhere is just equal to the surface concentration. And this thing is just called the effectiveness factor. And so what this means is that usually we like to talk about our rate of reaction, right, in terms of RA. Well, if our internal effectiveness factor is the overall rate of reaction divided by the rate of the reaction without any limitations, right? Well, this thing really is just RA. And so if we look at this then, RA, we can represent as just equal to the effectiveness factor times the rate constant times the concentration of A at the surface. Okay. Now, we've also talked this semester that it's very difficult for us to know what this is, right? And so there's two questions here that I have. One is, how do we get this in terms of the thing that we can measure, right? Which is just the bulk concentration of A. And the other question is, does that only involve internal mass transport? Of course not, because we spent a few lectures, and for a reason, talking about external diffusion as well. And that's something that we really have to seriously consider now that we are looking at these particles. So let me just do this really quickly, if you don't mind. So we have our catalyst particle. And in the last lecture, we only considered the fact that we might have internal diffusion. But the few lectures before that, remember, there's flow around this particle, right? It's in a packed bed reactor, right? And there's a boundary layer or diffusion layer thickness that is around this particle. And so now we have to consider multiple things when we talk about the reaction rate, right? We can be limited, of course, by just kinetics. We can be limited by the internal mass transport, and we also can be limited by the external mass transport. And so how are we going to use this fact to get this expression in terms of CA? Well, if you remember, we can only have our reaction occur as fast as we can diffuse the reactant towards the particle, right? That's the highest mass transport rate that we can have. And so when we talked about internal or external mass transport, we had an expression that said that the rate of the reaction, which was K1 times the concentration at the surface, equals Kc times AC times the concentration gradient, right? Ca minus Ca at the surface. But in that case, we just had a very hard sphere, right? We were considering the case where our particle looked like this, right? That there was no internal porosity. Okay. But now that we are considering that porosity, right? Well, we have a way to understand what the rate of the reaction is, especially taking into account that most of the surface area is actually inside the particle. So all we have to do to this expression that we already derived is modify it, right? Where the kinetic or the rate of reaction, right, which is now our effectiveness factor times K1 times Ca at the surface, is equal to the rate of the diffusion of the reactant towards the particle, okay? And if we look at this, we should be able to group the terms that have CAS, right? So this is Ca at the surface times the effectiveness factor times K1 plus Kc times Ac, and that just equals Kc Ac times the bulk concentration of A. And if we solve for Ca at the surface, of course, that's just Kc times Ac times Ca divided by Kc Ac plus the effectiveness factor times K1. Okay. And so this means that we can write the rate of reaction for A, because remember from up here, Ra is the effectiveness factor times K1 times CAS. So now Ra equals our effectiveness factor times K1 times Kc Ac over Kc times Ac plus the effectiveness factor times K1 times Ca. Okay. Now the nice thing is that essentially all of this stuff is going to be constant, right? Most of the time, especially for operating isothermally. It also looks very familiar. But to help us maybe understand what this is, we're actually going to take a subset of this and define this thing that we're going to call the overall effectiveness factor. All right, and it's going to be given the symbol omega, and it's going to be defined as everything in this term except for K1 in the numerator. So it's defined as the effectiveness factor times KCAC divided by KCAC plus the effectiveness factor times K1. Now, sometimes it's written a little bit differently than this. Sometimes what you'll see is that it's divided, both the numerator and the denominator are divided by KCAC. And when that's the case, that's just the effectiveness factor over 1 plus the effectiveness factor times K1 over Kc times Ac. And it's written that way because they want to give an overall impression of this ratio. They also, when it's defined this way, gives a nice relationship between the effectiveness factor and the overall effectiveness factor. So you'll notice this overall effectiveness factor can never be larger than the internal effectiveness factor, or just the thing called the effectiveness factor. And what this is really a measure of is that this is really the rate of the overall reaction divided by the rate of reaction if both the internal and external surface area were at the bulk concentration, right? So if the entire surface experienced the bulk concentration. Okay. And so now we have, basically from this definition, that Ra is just equal to the overall effectiveness factor times K1 times Ca. And being able to define the effectiveness factor this way actually really helps to simplify solving problems. You know, you might have thought, based on all of the math that we've done lately, that now solving for the behavior in a packed bed reactor might be extremely complicated. But that's not the case. You know, let's do A to B in a packed bed reactor. Well, dFA dV, right, or going back to the volume, right, is equal to this RA, which is equal to minus the overall effectiveness factor times K1 times CA. And we've also had practice this semester with other things. For example, if we wanted to have this in terms of the catalyst weight, right, we could do RA prime K1 prime, for example. Or we also could solve this equation with the aerial rates as well. And all of those are interchangeable. But for our conversation today, let's just stick to this because of our experience with plug flow reactors and then our early experience with packed bed reactors. You know, this solution should be comfortable to everybody, and then we'll extend this later on. And a few lectures ago, I believe it was lecture 22, we actually said that you could take FA and you could deviate slightly from our typical definition, which was just CA times the volumetric flow rate, and do CA times the cross-sectional area times the velocity, right, times the velocity. And also, of course, the volume is just the cross-sectional area times the length. And we derived an expression that we were able to extend to the left-hand side of this equation that just showed this becomes dCA dL, or dCA times U, right, times the velocity. And now that's the solution here is the same in style as it was before, except now we just have our overall effectiveness factor times K1 times CA. And if we have a constant volumetric flow rate, which we should here, right, because A goes to B, delta N is equal to 0. Now, of course, if delta N was not equal to 0 and it wasn't isothermal, right, so let's say it's isothermal and isobaric. If one of these weren't the case, just like in the last homework assignment, you guys would have to account for the change in temperature and in the velocity, right, through the volumetric flow rate. But let's just simplify things a little bit here. And if that's the case, we're just going to say that the velocity is just equal to the initial velocity. And then this equation just becomes the initial velocity dCA dL equals minus the overall effectiveness factor times K1 times CA. And rearranging this a little bit to integrate, right, dCA over CA just equals minus the overall effectiveness factor times K1 over the initial velocity, dL. And if we integrate over the length of our reactor, and we know that at the inlet we're at CA0, and we go to some arbitrary concentration further down the packed bed reactor, the solution to this is actually reasonably straightforward, right? This is the natural log of CA evaluated from CA0 to CA. And that equals minus the overall effectiveness factor, K1 over the initial velocity times the length. And of course, this is just the natural log of CA over CA0. And so we get a solution that looks very, very similar to what we've done before, that CA is CA0 times the exponent of minus the overall effectiveness factor times K1 over the initial velocity times the length, right? And that looks very similar to things that we've done a couple of times before. We also could solve this in terms of conversion. And to do that, we've already said that when the velocity is constant, it was because it's isothermal, isobaric, and there's no change of moles. So we know that CA is equal to CA0 times 1 minus X, or dCA equals minus CA0 times dx, right? And so our equation here, we can make two substitutions, one for dCA and the other one for CA, with these two functional forms that we have here in the upper right. So if we do that, right, this just becomes U0 times minus CA0 times dx dl equals minus the overall effectiveness factor times K1 times CA0 times 1 minus the conversion. And right, the negative signs cancel, the CA0s cancel, and we end up with a functional form that looks like dx dl equals the overall effectiveness factor times K1 over U0 times 1 minus x. Of course, dx over 1 minus x equals the same parameters on the right-hand side, just times dl. And now we're going to do a very similar integration to what we did before, except now, of course, that the inlet conversion is 0, and we're going to integrate to some arbitrary conversion. And we've solved this problem several times before as well. And you can get, of course, this just becomes minus the natural log of 1 minus x equals the overall effectiveness factor times K1 over the initial velocity times the reactor length. Or if we wanted to, we could just solve for conversion, right? We could say, well, then the conversion is equal to 1 minus the exponent of minus the effectiveness factor times K1 over U0 times the length, right? And hopefully that looks familiar as well, because we've solved equations like this several times throughout the semester. So even though now we're at this point where the concepts are more complicated, the math does not necessarily have to be, or at least not the primary math. We are going to have to do some other things in order to know which form of the equations that we're going to need to solve, etc. But we don't end up with these crazy complicated functions. We end up with things that are very similar to functions that we're hopefully comfortable with. So I noted above, right, when we were talking a couple minutes ago, that we really have 3 cases that we have to consider here, okay? Or at least we have 3 possibilities for what could be limiting our reaction, right? We could be kinetically limited, right? Or what I really mean by that is the surface rate is limiting. The other thing that could be limiting is internal mass transport, and the other one is external mass transport. Okay. And what happens to our expression that we had above, where minus RA is equal to our effectiveness factor times K1 times KC AC over KC times AC plus K1 times the effectiveness factor for each one of these cases, okay? So we're gonna call this case 1, case 2, and case 3, okay? So let's have a look at this and think about this a little bit. So let's do case 1, where we are surface rate limited. So if we are surface limited, well, one of the things that has meant to us before was that K1 was much smaller than KC, right? That's the first thing that we noted. When our surface rate was the limiting process, that the mass transport coefficient was greater than the reaction rate constant. And that's something that you got to see the balance of in the homework that was due. Now, in the context of what we've done between the last lecture and today, that also means that if the surface rate was limiting, that the concentration inside of the particle would be equal to the bulk concentration, right? This is our discussion about the small value of the Thiele modulus, right? So that would mean that the Thiele modulus is small, or a different way to maybe think about this that might make sense is that our internal effectiveness factor is equal to 1, right? That the concentration inside the particle is about the same as whatever the concentration on the surface is. And when K1 is much less than Kc, this really simplifies quite a bit, because if you look at this expression for minus Ra, when we have K1 far less than Kc, well, what's the first thing that happens? That goes away, right? Because K1's very small. Now all of a sudden we have this expression that is the effectiveness factor times K1 times AC times, and I apologize, guys, that this was Kc times AC times Ca over Kc/AC. So now that means this cancels with this, that cancels with that, and we were told then the effectiveness factor was approximately equal to 1. So that goes away. And so when we are surface rate limited, what that means is that we can use the same expressions that we've used the entire semester to describe the kinetics. It's simply equal to K1 times Ca, which is really nice. And what we'll, as we move forward, and we'll spend most of the time in the next lecture doing this, is we're going to now find ways to calculate the effectiveness factor so we know what we have to take into consideration. Okay, but I think hopefully that would make sense, that if we are kinetically limited, that we should get an expression that looks very familiar from where we started before we ever even thought that mass transport might play a role in the process. Okay, so now let's look at case 2, when we are internal mass transport limited. Well, or sorry, external mass transport. Well, I guess we can do either one. Let's do internal mass transport limited. So when we're internal mass transport limited, all that we really know then is that the effectiveness factor is small, right? We're not using the catalyst at all. So when the effectiveness factor is very small, essentially what happens is that the denominator here, this first term is going to, or sorry, the second term in the denominator is going to go away. And again, you're going to have the Kc are going to cancel, the ACs are going to cancel, and you end up with a functional form where Ra is just equal to the effectiveness factor times K1 times Ca. And again, hopefully that makes some sense. And in the third case, where we are external mass transport limited, so what's going to happen here? Well, if we're external mass transport limited, this means that K1 now is much greater than Kc, and it also is going to mean that our effectiveness factor is approximately equal to 1. And when that's the case, now in the denominator, the term that is going to go away is this one. And then you're left with K1 times the effectiveness factor in the denominator. So the effectiveness factors even cancel, and then the K1s cancel. And so what we're left with then is that Ra equals Kc times AC times Ca, which is exactly what we had a couple of lectures ago when we were talking only about external mass transport. And so the trick here in the problems that we're going to be solving here over the next week or so is that we're going to need to determine, using the values for the effectiveness factors, which one is controlling here. Is it internal mass transport, external mass transport, or is it the surface rate? And then when we know that, we know which form of the rate law we are going to utilize. Okay. Now, before I move on and do one more thing for today, I wanted to just open this up and give you guys the chance to ask any questions that you have about the effectiveness factors or how I did any of the simplification here. Okay. All right. If there aren't any questions, let's do the last thing that we are going to do this morning. One of the important things I think to take away from our class is then how would you use experimental data to understand what is going on inside of a reactor? So how would we look at experimental data and understand what process was the limiting process? Okay. And for us to have that conversation, I think we need to think about what each of the important parameters are really a function of. Because in our expressions above, we had K1, which was our reaction rate constant. We had Kc, and you remember the velocity and the particle diameter are in Kc. We had Ac, which also houses the particle diameter. And then we had the effectiveness factor. And remember, the effectiveness factor is going to be related to the Thiele modulus. And the Thiele modulus has K1 in it. It also has R. It also has the diameter of the particle or the radius of the particle in there. So I would like for us to, I think, make a table and then start to understand what we might expect out of experimental data. And then in the next lecture, we're going to do examples where we look at experimental data and then we try to figure out what process is controlling when. Okay, and so I mentioned 3 variables, and we know we have 3 possible processes that could be controlling our reaction rate. Okay, so let's look at those. So the 3 parameters, right, were flow rate, particle size, right, or the particle diameter, and the other one is temperature. And here we are kinetic limited or reaction limited, right? And then we can do external mass transport and internal mass transport, okay? So if we think about this, where things are reaction limited, right? We have K1. What is K1 a function of? Does anyone want to come in and tell us, you know, what we've been, I think we've only used 1 variable so far. So what's K1 a function of?
Temperature.
Yeah, just temperature. And we know that that dependence is exponential, right? That it's always K1 is equal to K10 times the exponent of the activation energy over RT, right? So it has an exponential dependence, okay? Good. Now that also means that it's not dependent on the particle size. It's not dependent on the velocity or the flow rate. All right, great. So now let's think about when we are external mass transport controlled. Well, when we're external mass transport limited, we have this thing Kc times Ac, right? And if you remember that Kc, we've actually come up with an expression before that Kc is actually proportional to the velocity to the 1/2 divided by the diameter of the particle to the 1/2. And that derivation we did a couple of lectures ago. And remember, AC was a form factor. And for spherical particles, it was 6 times 1 minus theta, you know, the porosity, divided by the diameter of the particle. And so that means that AC is proportional to 1 over the particle diameter. So now when we're external mass transport controlled, we are definitely dependent on flow rate, right? So we are absolutely that the external mass transport rate is definitely influenced by the flow rate and at the tune of the velocity to the 1/2. We also here know that we're absolutely influenced by the particle size, and that is by the diameter of the particle to the 3/2, right? Because 1/2 times 1 over the diameter of the particle is 1 over the diameter of particle to the 3/2. Now, temperature is a little bit more complicated because we don't have an Arrhenius function that we have to worry about for Kc or AC. But Kc does contain other parameters like the diffusivity, for example, the kinematic viscosity. All of these are functions of temperature. But how? And without getting overly complicated, it all kind of averages out that the temperature dependence is approximately linear. Okay. Now let's go to internal mass transport. So internal mass transport, the boundary condition on the outside is influenced by the concentration at the surface. But if you're internal mass transport limited, the concentration at the surface becomes very similar to the bulk concentration. And what that means is that if you keep flowing faster and faster and faster, or if you were to back off even on the flow rate, it really wouldn't change anything, right? You're internal limited. So everything that you do outside of the particle doesn't really matter. So you're not really dependent on the flow rate for internal mass transport limited processes. Now, these last two are kind of interesting. So if we think about internal mass transport limitations, well, we came up with the Thiele modulus. Now, we haven't actually talked about how we can quantitate the internal effectiveness factor or the effectiveness factor using the Thiele modulus. We're going to use that in an example next time. We'll use it in the homework. So I'll give it to you here and then we'll just talk about it later. And that is that our effectiveness factor can also be calculated by a very simple equation, at least for this first order reaction, where it's the Thiele modulus squared times the Thiele modulus times the hyperbolic cotangent of the Thiele modulus minus 1. It's just, that's on page 731 in your book. If you want to have a look at exactly where that comes from. But I don't want to spend the 10 minutes to derive the equation. I just want us to have a conversation about it. So let's say that that this is fairly large and this goes away. Essentially what that means is that for our perspective, that the effectiveness factor is something like proportional to the Thiele modulus over the Thiele modulus, or the square root of the Thiele modulus over the Thiele modulus, or 1 over the square root of the Thiele modulus, right? And we know from our discussion last time that the square root of the Thiele modulus is equal to R times the square root of K1 over the effective diffusivity. So this essentially means that this is just equal to the square root of the effective diffusivity over K1 times 1 over the radius. So if that's true, then our effectiveness factor is definitely influenced by the temperature, right? Because it's K1, and that's exponentially dependent on temperature. And the square root of the exponential doesn't really affect anything here. We also can go back to this equation here, where we are internal effectiveness limited, and you see that we also have a direct formulation of K1 in the rate law. So, K1 is there. The other thing that we have here is the diameter of the particle, right? Right here, actually in the denominator. And so we do have a dependence on the particle size, 1 over the particle diameter. And hopefully that makes sense to everybody, because if you're internal mass transport limited, one of the ways that you can influence the rate of mass transport is to reduce the distance over which you have to do the mass transport. So we did that in external diffusion by increasing velocity. But for internal diffusion, if you just made the particles smaller, you would do the same thing, right? The distance that you would have to diffuse internally would be lower. So the overall rate into the particle would be higher. Okay. So in our next lecture, we're going to take a look at some experimental data, and we are then going to use that data to understand in which regimes might we be controlled by the reaction kinetics or external mass transport or internal mass transport.